Hello students, now in this lecture we are going to study about Fourier's law of heat conductions and some formulas regarding to heat conduction through wall and pipes. In last lectures you have learned about what is meant by heat transfer and the different modes of heat transfer. In these lectures now we are going to study about the base on which the all modes of heat transfer is based, and that is nothing but the Fourier's law of heat conduction. To understand the concept of heat conduction, Fourier performed an experiment. He had taken a plane surface wall which has a cross-sectional area A and thickness x. Later on, he supplied heat Q to one side of the plane surface and maintained the temperature of the either side of a surface as T1 and T2 as shown in the figure respectively. One point is to be noted that the T1 is greater than the T2. If you observe this figure carefully, you have noticed that the wall is made from the height h and width w, due to which there is a cross-sectional area A is becomes, and there is a L is thickness of that wall. From one side of that wall, Fourier started to supply heat Q, which is shown by the dark pin arrow, and after some times he had noticed that heat will be transferred to another side of a wall. At the one end of the wall there is a temperature is T1, and at the another side of the wall there is a temperature T2. The question in mind that how is the heat transfer from this one surface or one side to another sides. You can observe that there is a transfer of heat takes place from one surface to another surface or opposite surface through a dark pin arrow, but this is not an actual way of a heat transfer. The way of a heat transfer takes place by a tapered lines between these two temperatures, which is shown by the small pink line in a figure. Before going to make any conclusion from this experiment, Fourier had made few assumptions prior to conduct these experiments, and these are the following few assumptions. First one is that conduction takes place under the steady state condition of the heat transfer. Steady state condition means nothing but the rate of change of temperature with respect to time remains constant. Second assumption is that the heat flow takes place only in unidirectional, means there is a transfer of heat from one side to another side of the plane in a only straight line manner, not in a zigzag or not in a curvature manner. Remember, one point is that the flow of heat is always unidirectional, means there is not any possibility of return back of heat flow. Third assumption is that there is no any internal heat generations. That means when we are the heat supplying heat from one surface to another side of a surface, there is no any internal heat generation through that surface. And last, fourth assumption is that the material of a surface is homogeneous. That means cross-sectional area of a wall is made from a single material throughout its area, and it does not contain any type of impurity. After conducting the experiments, he stated the law of heat conduction that the heat transfer through this plane homogeneous surface is directly proportional to the cross-sectional area, directly proportional to the temperature difference, and inversely proportional to the thickness of that plane surface. Mathematically, he expresses this statement is that Q is directly proportional to A. Q is directly proportional to delta T. Delta T is nothing but the temperature difference, that is T1 minus T2, and Q is inversely proportional to delta X, that is nothing but thickness. Equating all these three equations, he developed a formula that is Q is directly proportional to A into delta T divided by delta X. To remove the proportionality signs, he developed the equation is Q is equal to K into A into delta T upon delta X. But you can observe that in the equation there is a negative sign. So that negative sign is indicates that the temperature decreases as the thickness increases. You can observe that if the value of thickness goes to increases, the value of temperature T2, that means the temperature at either side of the surfaces, goes on decreases. Hence there is a negative sign in the equation. The ratio of delta T to the delta X is known as temperature gradient. In this formula, K is called as the thermal conductivity of a material. From these all mathematical expressions, finally we get the formula for calculating the K, that means thermal conductivity of the material. And to obtain these equations, we are just shifting the terms from the equation of a Q. And finally we get the formula for thermal conductivity is Q into delta X divided by A into delta T. Now, from this equation, thermal conductivity of a material can be defined as the amount of energy conducted through a body of unit area, unit thickness, in unit time when there is a unit temperature of difference between the phases. Remember, the unit of thermal conductivity is watt per meter Kelvin or watt per meter degree Celsius. One point is to be remembered that the material with high value of a K or high value of thermal conductivity is called as a good conductor, while the materials with lowest value of a K is called as an insulator. Student, I hope you understood the concept of thermal conductivity of a material. Now this thermal conductivity of materials depends upon the following some parameters. First one is chemical composition. Pure metal shows the highest value of conductivity. As the impurity or alloy formation increases, conductivity decreases. That means the pure metals like a copper, zinc, aluminum, these are the pure metals which are homogeneous, shows the highest value of conductivity. But if there any alloy content element is increases in that material, conductivity decreases. You can observe that the thermal conductivity value of alloying elements like brass, bronze, hindallium, steel comparatively less than its their pure compositions like copper, aluminum, iron, etc. Second is mechanical forming. Any mechanical operations or heat treatment reduces the conductivity of materials. Third, temperature rise. Rise in the temperature of any material decreases its value of conductivity. Fourth one is presence of air. Conductivity of any particular material presence decreases if there is a presence of any air. Last one is density. Conductivity increases while rise in the density of a material. Student, we are going to study the thermal conductivity of a material through walls and pipes. Consider a plane section of a wall in front of you which has a cross-sectional area A and thickness X. Now by supplying the heat Q from one side of the wall, you can observe that after some period of time, at the another side of the wall there is also a formation of a heat or transformation of a heat. So due to these transformations, at the front side of the wall temperature is T1 and on another side of the wall surface there is a temperature is a T2. This wall is made from a single material throughout the sections, hence this wall is called as plain wall or homogeneous wall. Look at the right hand side figure. This is the side view of that wall in which small section of a thickness of wall is considered to be delta X and due to which there is a temperature differences occur delta T. According to Fourier law, we have a equation of Q, that is minus Ka into delta T upon delta X. Now we are going to reshuffling the terms of this equation. Here is to be considered that the thickness and the temperature, these both parameters are variables. That is, your thickness changes from x is equal to 0 to x is equal to x, and the temperature is changes from T1 to T2. So T1 is called as the initial temperature and T2 is called as the final temperature. As shown in the slides, we are going to arrange the Fourier's equations in a balance equation like that Q into delta X is equal to minus K into delta T. Now in both sides of the equations there are variable parameters. Hence we are going to integrate the both side of equation. Just see the equation after application of integration. By solving integration, we have a equation that is Q into X is equal to minus Ka into T. And putting the value of limits of integrations, we have equation Qx is equal to minus Ka T2 minus T1. But to remove the negative sign from the equations, we rearrange the term of equation as qx is equal to ka into bracket t1 minus t2. So at last we have a formula q is equal to k into a t1 minus t2 divided by x. Rearranging the term, we have a second equation, that is q is equal to a into bracket t1 minus t2 divided by x upon k. And this is a formula for the conductivity through plane wall. If surface wall is made from two or more different materials, or if a plane wall of a surface has a certain layer of thickness over it, then such type of wall is called as a composite wall. This is the side wall of a composite wall, in which that is the first one is the basic walls and second one is the coating of a certain thickness over this wall. Hence this section of a wall has two different values of conductivity, K1 and K2. K1 for the basic material wall and K2 for the coating materials, and two different values of thickness, that is x1 and x2. In this case, you will get three different values of temperature. T1 is innermost temperature, T3 is the outermost temperature, and T2 is the junction or intermediate temperature. Here the value of temperature decreases from T1 to T3. By applying the concept of plane wall to these equations, ultimately by solving the equation, we have a new formula for conductivity through composite wall, and that formula will become as q is equal to a into bracket t1 minus t3 divided by x1 upon k1 plus x2 upon k2. One point is to remember that the terms utilized in denominator is increases as the number of coating thicknesses increases in a composite wall. Now we are going to study about conductivity through hollow pipe. Now consider there is one hollow pipes which has an inner radius R1 and outer radius R2, and the length of that pipe section is L. Now that pipe section carries a hot fluid in such way that the inside temperature of that pipe is T1 and outermost temperature of that pipe is T2. As I told you that the heat flow through this pipe from one end to another end is along the circumference of the section of a pipe. Hence, in this equation, or in this case, we can consider the circumference of a pipe as a 2 pi r L instead of its cross-sectional area. Look at the diagram. This shows that how the circumferentially heat is transferred from one end to another end. Now applying the Fourier's conductivity equation to that concept, there is some changes in that equation, and in that case instead of dx we are considering the mean radius of that section. Hence instead of dx in these equations we have a term dr. So our equation becomes q upon a is equal to minus ka into dt upon dr. Now in this case, radius and temperature, both parameters are variable. That means radius changes from R1 to R2 and temperature is also changes from T1 to T2. Rearranging the terms of parameters in these equations, q upon 2 pi rl into dr is exactly equal to minus k into dt. At both sides of the equation there are two variable properties. So applying the terms of equation to that properties, ultimately we have equations, and in that equations we have a logarithmic value of a parameters. By solving the terms of equations through this formula, ultimately we have the new formula for conductivity through pipe, and that is nothing but q upon 2 pi L is equal to k into bracket T1 minus T2 divided by log base raised to R2 upon R1. Arranging the different terms, we have the two different formula as shown in the figure for thermal conductivity through pipe. Now, if any cross section of a pipe carries a number of layer of coating from its outside, then radius of curvature of that pipe section is increases. Such type of pipe is called as a composite pipe. As shown in the figure, you can see that this pipe sections each has a one layer of coating, so that its radius is also increases as a R3 from the center of a pipe. So such type of pipe is called as a composite pipe. In this diagram you can see that there is a layer of coating, so that the pipe section has another radius, that is R3, that is outermost radius, and above that outermost radius there is a outermost temperature T3. So you can see that in the formula of thermal conductivity through pipe, in that formula, in the case of denominator, there are term of denominator is increases, and logarithmic radius of that section is also increases. One point is to be remember that as the number of coatings are increases in the pipe sections, then the number of radiuses are also increases, and simultaneously the ratio of logarithmic radius in fact formula is also increases. Now student, there are some few questions regarding to this topic. Solve this question in your notebook.